Welcome to the video that's going to walk us through an example problem for systems. That means we're going to apply Newton's second law for two or more objects that are connected together. All right, and this approach will be the same approach that you're going to use whenever we have multiple objects connected and you need to use Newton's second law to figure out how or in what way the objects are moving. Before we jump right into the problem, a couple reminders about our strategy. The strategy for the most part isn't changed in terms of applying Newton's second law. There's just one or two things you need to be aware of. The first is just simple. Make sure you recognize if there is just one object or if there are multiple objects that are moving together. You should draw coordinates, choose your positive and negative, and you could sometimes even draw different coordinates, one for one of the objects, one for the other. I'll show you that in a sec. All right, you want to draw those free body diagrams, and you want to do it for each object. Break things down into components if you need to, and then set up the sum of the forces in the x and in the y direction. So here's our example problem. It says I have two blocks. There's M1 and M2. And these blocks are connected by a string. We'll ignore any kind of mass. This right here is a pulley. Okay, we'll assume there's like no friction in the pulley. So these blocks are free to accelerate because there's also no friction on the table. And there's no numbers here. All right, we're just going to use the second law to show the basic setup and approach for this problem if we were trying to write an equation or equations for these objects' accelerations. You may have just heard the class bell go off behind me. Anyway, let's go over our strategy. Strategy step 1, identify the system. Easy, this object and this object. I'm not even going to write anything down. Step 2, if I go back and remind myself what step 2 says, draw a coordinate system. Well, here's where we get interesting. Here's where things get interesting. This orange block is going to start moving to the right because the green triangle is going to be tugging on it. I'm going to say for the orange block, and I'll use an orange pen, I'm going to say to the right is positive. And, you know, usually up is positive, so I'll do that here. All right, let's look at the green block. There's no friction. So when this block starts moving to the right, the green triangle is going to start moving down. Now, you could say down is negative. That's what we usually do. But I'm actually going to say that down is positive. Okay, downward is the positive direction. I really messed up that triangle. Let me try and redraw it. Okay, downward's going to be positive for this triangle here. All right, but there's my coordinate system. I'll show you why this is going to come back and help us later. Next step, that was step 2. Step 3, draw a free body diagram for each separately. All right, well, let's start with orange. I'm going to write actually object M1. Here's my free body diagram. I know there's an upward force. That's the normal force for M1. I'm going to use N just so I have less things to write down. And the weight or gravity, that's the weight of M1. And there's also a force acting to the right. I'm going to call that tension because it's from a string. Usually we call that force a tension force. That's it. There's no friction. So that is my free body diagram. For object 2, object, that's an E, M2. Look how nice and organized I am. Free body diagram. Well, I know there's the weight of M2. And, well, there is this string here. It's connected. There's this tension. Oh man, something interesting. This tension here is equal to the orange tension. How do we know that? That's from the third law. That might be helpful in problems where there's numbers because those two tensions have to be the same thing. You might be able to use them when you're plugging in and solving. Okay, this mass here is being tugged up. This block here is being tugged to the right. By the third law, these two forces are equal and opposite. They're being exerted on each other. The next thing I actually really want to highlight is that M2 is not in free fall. Okay, it is not accelerating at 9.8. A lot of people think, well, that triangle or that object is just going to be falling down vertically. And it's true that it's going to be moving vertically, but there's this upwards tugging force that's acting on it. There is a force that's going to take away from the weight that's usually pulling it down. So don't think just because this green triangle is moving vertically, even though there's no friction. Okay, this triangle still has to tug on the mass's inertia. This weight force has to make this one accelerate too. Okay, the green triangle will not be falling downwards at 9.8. Don't make that mistake. Okay, you still have to tug on this box, and that box has a tendency to keep what it's doing. It's laziness, it's inertia. All right, anyway, here's the free body diagram for my two objects. I'm going to go to a new fresh screen that doesn't have some of this stuff, okay, and I'm going to copy over these free body diagrams to do the next step. The next step is to, well, break any forces into components. I'm going to skip that. I don't need to. Everything here is acting in our usual X and Y direction. So, okay, I don't have to worry too much about number 4. Number 5, breaking things in, or I'm sorry, using Newton's second law, doing the sum of the forces. So I'm going to go right here. I copied over those free body diagrams for orange. I'm going to go back to orange. I'm almost going to keep these separate the whole way. Here I go. The sum of the forces. This is for block M1 in the X direction. Well, there's no friction, remember. So I have tension, and I said this way was positive. For green, remember I said down was positive. That'll become obvious soon. Well, in the X direction, if there's only that tension, that must equal M1 times A. Technically, this is like the acceleration of object 1, but remember, these two things are a system. They're moving together. They're going to have the same acceleration. So you can leave that if you want, but they're going to have the same acceleration, so I have that. Sum of the forces in the Y direction. Well, I have the normal force of M1 minus the weight of M1. That equals MAY, and that equals 0. I know the normal force of M1 equals the weight. Okay. Well, let's go on this side. Let's look at the sum of the forces. I'm not even going to do X. Okay, if it's not clear why, there are no forces in the X direction. Notice I'm nice and separate. I color-coded. I recognize you probably can't do that on paper, but clearly label which objects you're doing. That's going to help you out. Well, I know there's tension. And let's see. I said downward was positive. So this tension should actually be a negative value. Now I'm going to add the weight of M2, and that equals M2. Remember, they have the same acceleration. In purple, over here, if up was positive, if I was to set up the sum of the forces for that triangle, it would look like this. Tension minus WM2 equals MA. And if you wrote this, you would have a problem. Because, yeah, you're following convention. You're saying up is positive here and weight is down. But this green triangle is not going to accelerate in the positive. It's going to accelerate in the negative. You would have to artificially put in a minus A. Because again, this green block is going to move downward since there's no friction here. All right, it's going to be tugging downward due to gravity. So if you use upward as positive and the object is moving in the opposite direction, you got to flip it. That's why I always like making the direction the objects move as the positive direction, because then I don't have to double check and make sure I have a positive or a negative there. If you set this up, you are going to get incorrect answers if you were like swapping and putting things into different places. Okay? To be honest, there's not a whole lot I could do here any further. All right, maybe if there was friction acting on this block, this might come into play because I know the frictional force is based on that normal force and that coefficient. Okay, but that's not really taking place in this problem here. I know those tensions are equal, so it's possible that I could plug one into the other depending on what the problem says. So since the third law says those forces are equal, I might be able to swap them back and forth. But here's an example of me just setting up both the free body diagram and Newton's second law. Stay organized. Keep things nice and separate. Thanks for watching.